In SPC3, we're going to have a look at voltage current graphs. So these are spawned off of Ohm's law. So the bits hinted at here, this in particular is Ohm's law, so R equals V over I, or V equals IR. And we're going to have a look at what happens when we plot a voltage against a current, so a voltage current graph, as I say, and see if we can get anything useful out of that. So when we say plotting the voltage against the current, what voltage and current is it we're talking about? Let's say we've got ourselves a simple circuit, so we're going to have a cell. We're going to hook that up to some sort of load, so that might be a resistor, it might be a bulb, some scientific instruments, whatever it is that the cell's powering. We're going to stick an ammeter in there, and we're also going to stick a voltmeter across the load. So we'll be able to measure at any given time what's the current passing through this load using the ammeter, but also what's the voltage that's across the load. And in order to get a graph, we're going to have to vary something, and so what we'd have is we'd have a power pack or a power supply that we can vary the voltage on, for example. So we might have something that goes from 0 to 5 volts, and as we vary that, we're going to change the voltage that this is putting out, and therefore the voltage that's passing across this load, and we can measure the corresponding output that we get from that. Lies. So let's have a look at what we get. So let's see what Ohm's law tells us we'd be expecting from this. So now we know what voltage and current it is we're measuring, we can clear that. And let's get back to Ohm's law. So V equals IR, nice and simple. And so when we're plotting graphs, we like to have nice straight graphs. Let's see if we can compare this against the equation for a straight line graph. So y equals mx plus c. We can see straight away that there is no plus c, so that's going to have value 0. There's not going to be a y-intercept on the graph that we would expect anyway. And then these two have been kind of flipped the wrong way around. So if we were to rewrite Ohm's law to line up with this, we'd have V equals RI. So we're going to plot the voltage against the current, and M, the gradient, is going to give us the resistance. So if we quickly sketch out a voltage current graph, so we'd have the voltage in volts, and we'd have the current in amps. And so what this tells us we're expecting is a perfectly straight line, or close enough. And so the gradient would give us the resistance of the load that we were measuring the current and the voltage across. So the little circuit diagram we had sketched out earlier, the resistor, this gradient would be the resistance of that resistor, and we'd expect it to pass through 0. We said there's not going to be a y-intercept. If this is indeed the graph that we get when we plot voltage against current, then this is known as an ohmic conductor, because the straight line we have here means that it follows Ohm's law, that the voltage is directly proportional to the current. In the experiment you'll do this lesson, you'll see that voltage current graphs can come in all sorts of different shapes, and not all components are going to follow Ohm's law and give us this straight line. We'll get all sorts of other shapes as well, which you'll see. While we're on graphs, we're also going to take the opportunity to have a chat about variance, about uncertainty and random errors and the like. And so when we plot a graph, you won't get a perfectly straight line like that. What you'll actually get is something like this that you've got in your notes. So here we can see we haven't got a perfectly straight line. We can see it's probably meant to be a perfectly straight line. It's unlikely, certainly if we have a look at this one, it's unlikely that the graph really follows these points, what we've got is we're expecting a straight line, we've got a little bit of uncertainty. So this one's maybe been measured slightly higher voltage than it should have for that current, and this one's maybe been measured at a slightly lower voltage than it should have for this current. So let's have a look at where these problems come in. So one of the issues can be limited precision. So if, say, we've got a ruler, something nice and straightforward, take a step away from the circuits, if our ruler only goes down to 1 centimetre increments, we're not going to do a very good job if we try and measure something to the nearest millimetre. We'd only be able to measure to the nearest centimetre with that ruler. And so similarly, where we've got our voltmeter or an ammeter or a multimeter, we're going to be limited by the amount of precision which that gives us. It might be perfectly adequate, but if we're only getting, say, one significant figure out of our instrument, then that could potentially introduce some quite large errors. We can also have random errors in the equipment and the sample, etc. And so, for example, the power pack, where we were varying the voltage, maybe it's not able to put out a steady voltage. Maybe that voltage is going to vary slightly over time, and that's going to introduce a little bit of uncertainty, because if we measure it when it happens to be putting out a slightly higher voltage compared to when it happens to be putting out slightly lower voltage, we're going to get different values. So what does this look like? I've plucked a pair of graphs here off of the web here. We've got one on the left and one on the right, and so these are measurements from the same experiment, only with different amounts of measurement. And we're going to see why it is that we get a bit of a difference. And so the limited precision that we spoke about earlier, there's not really much we can do about that without getting better equipment. So if our ruler only goes down to centimetres, we're not going to be able to measure in millimetres until we go out and get another ruler that does measure down to millimetres. Similarly for our multimeters, once we reach the limit of the precision of the equipment, we can't really overcome that without getting better equipment. But the random uncertainty can be helped, and so that's what these graphs are demonstrating. And so there's the average, which we can see. So over here on the left, we've only got a couple of values. On the right, we've taken many measurements. And so on the left, we expecting the average to be dead center here, and actually it's come a little bit off center because we've got so few measurements that the few that happen to be a little bit high have skewed it into the higher region. Whereas once we've taken many measurements, as we have on the right, you can see the average is falling almost dead center as we'd expect. And if any of you have done this in stats, the standard deviation can also be seen to be much broader on the left graph than it is on the right graph. So on the right graph, these many measurements allow us to narrow down the standard deviation compared to what it is on the left. And so not only can we say we think the mean value is this, so we think the resistance has this value, we can say, well, there is a bit of variance, and so there's a bit of uncertainty. We could say it's this value, but it could be as high as this, or it could be as low as that. Whereas over here, our mean is a little bit higher, and if we were going to take the same standard deviation, we're going to have much wider regions. And so taking multiple values and averaging them helps us. If we're plotting graphs, there's another trick we can do. Here we can see another graph again. This isn't a voltage current graph, but what we can do is, as well as doing our line of best fit, we can do a line of worst fit. So here you can see each plot, each point has got an uncertainty represented by the height of these bars. So this point here was measured to be this value, but it could be as low as that, or it could be as high as that for the equipment and the conditions it was measured under. So if we nip over here, let's get rid of our line, and let's say now instead of our line we've just got a few points, and so we've got, let's say, one here, one here, one here, one here, one here, and another one here. So if we were going to do a line of best fit, we'd probably just do something straight up the center. We do it with a ruler, of course, but there's our line of best fit. That's what we think is the straight line. And so we'd say, in this case, this is what we think our resistance is. But clearly the points are a little bit scattered, and so the resistance could be a bit higher or it could be a bit lower. And so what we also do is we plot lines of worst fit. And so we say, well, yeah, this is what we think is the best fit, but we could also do a line like that, and that roughly fits the data. And we could also do a line like that, and that roughly fits the data, and we can see that these have got different values. So this shallower gradient would give us a lower value of the resistance, this steeper gradient gives us a higher value of the resistance. And so what we'd say is we think it's this value, so this central line that we've got here, we say we think the resistance is this, but it could be as high as this, or it could be as low as that, and so that's how we would represent our uncertainties there. So that's all that we're doing in SPC3. We're doing our voltage current graphs. We're having a look at what Ohm's law predicts, which is a straight line. But in the lesson, you'll do some experiments and see that we get other values. And we've had a look at the sources of variance of random error and some of the things which we can do to try and control that, either by plotting lines of best and worst fit, or as we did here, just by taking lots of measurements and taking the mean and the like.